Tonight, we're going to explore one of the strangest and most violent creations in the universe: neutron stars. They look small, they look simple, and most of the time they sit quietly in the darkness. But everything about them breaks the rules of normal physics. These stars form when massive suns collapse under their own weight, crushing matter into a state so extreme that atoms can no longer exist. A neutron star is not a normal object. It is what happens when the universe forces matter into its most compressed form without allowing it to become a black hole. It is a place where gravity, density, magnetism, and rotation all reach levels that no human mind is naturally prepared to imagine. Tonight, we're going to look at how these objects form, what they're made of, what they can do, and why they stand as the last stable form of matter before reality collapses further. This is the universe pushed to its limit, and neutron stars are the result. Neutron stars begin long before they exist, inside the cores of massive stars that burn brighter and faster than anything we see around the sun. These stars live brief, intense lives, spending millions of years in constant pressure against gravity. Their cores stay balanced only because nuclear fusion pushes outward with incredible force. But this balance cannot last forever. As the star ages, its core gets hotter and denser, and each stage of fusion creates heavier elements that bring the star one step closer to collapse. Eventually, the core produces iron, and that moment is the breaking point. Iron cannot release energy through fusion. When iron appears, the star reaches a dead end. Fusion slows down, gravity pushes inward, and the balance the star held for millions of years disappears in seconds. The collapse that follows is one of the most violent events in the universe. The core falls inward at a quarter of the speed of light. Temperatures rise to unimaginable levels. Electrons are crushed into protons, forming neutrons in a process that rewrites the structure of matter. The pressure becomes so extreme that atoms cannot survive. Their electrons are forced into the nuclei, stripping away everything familiar about normal matter. For a moment, the core becomes a superheated soup of particles collapsing toward a state no star should ever reach. Then, suddenly, the collapse stops. Neutrons cannot be compressed any further without breaking the laws of physics. The core stiffens. The outer layers crash inward, rebound, and explode outward in a supernova brighter than entire galaxies. What remains at the center is a neutron star. Small, dense, and impossibly strange. A neutron star is usually around 20 kilometers wide, no larger than a small city. But inside that tiny sphere is more mass than the sun. A teaspoon of neutron star material would weigh billions of tons. The density is so extreme that comparing it to anything on Earth becomes meaningless. Matter in this state cannot exist under normal conditions. It remains stable only because the star's intense gravity pushes inward while neutron degeneracy pressure pushes outward. That pressure is the final barrier nature offers before total collapse into a black hole. If a neutron star gains even a little too much mass, the barrier fails. The star collapses further, and a black hole forms. This razor-thin balance is what makes neutron stars so fascinating and so terrifying. They represent the final line between stable matter and complete gravitational collapse. Although neutron stars are small, they rotate with breathtaking speed. When the star collapses, its original rotation doesn't disappear. It intensifies. The shrinking core spins faster, just like a figure skater pulling their arms inward. Some neutron stars rotate dozens of times per second. Others rotate hundreds of times per second. A star-sized object spinning hundreds of times each second is a level of violence that the human brain is not built to visualize. These rapidly rotating neutron stars are called pulsars, and they act as cosmic lighthouses. Their intense magnetic fields produce beams of radiation that sweep across space. Every time the beam crosses Earth, we detect a pulse. These pulses arrive with such precision that pulsars rival atomic clocks in accuracy. Their timing is stable enough to detect gravitational waves and distortions in space-time. A rotating city-sized star behaving like a perfect clock is one of the universe's strangest gifts. The magnetic fields of neutron stars are even more extreme. They can be trillions of times stronger than Earth's magnetic field. The strongest neutron stars, called magnetars, possess magnetic fields so intense that they can tear atoms apart from thousands of kilometers away. A magnetar flare can release more energy in a single second than the sun emits in 100,000 years. Some of these flares have been powerful enough to disturb Earth's atmosphere, despite being thousands of light-years away. These magnetic fields twist, snap, and reconnect in violent bursts that rival the most extreme events in the universe. Standing near a magnetar would be impossible. Its magnetic field would erase your molecular structure instantly. The surface of a neutron star is another place where normal physics fails. Gravity on the surface is so strong that any object falling from 1 meter above the ground would hit with the force of a nuclear bomb. The crust, though only centimeters thick, is the strongest material known. It is so rigid that cracking it releases starquakes that shift the rotation of the entire star. Light escaping from the surface bends so strongly that you can see more than half of the star at once. And time itself flows more slowly near the surface due to the intense gravitational field. This is general relativity operating at one of its highest extremes, where space and time warp visibly around a dense object. Inside the star, matter enters exotic states that no laboratory can reproduce. The outer crust contains a lattice of atomic nuclei packed closer than anything found on Earth. Deeper inside, electrons are forced into protons, creating a super-dense fluid of neutrons. These neutrons behave like a superfluid with zero viscosity. They can flow without resistance, form quantized vortices, and store rotational energy in ways that produce sudden glitches in the star's spin. These glitches are one of the most mysterious behaviors of neutron stars. They suggest that the interior is not a simple fluid, but a complex structure of superdense layers moving independently from the crust. Even deeper, the pressure becomes so overwhelming that neutrons may break down into their components, quarks and gluons. If this happens, the core of a neutron star becomes a quark-gluon plasma, a type of matter that last existed microseconds after the Big Bang. It is possible that inside every neutron star is a pocket of the early universe, hidden beneath a crust only kilometers thick. This idea is not yet proven, but it shows how neutron stars push the boundaries of physics. They may hold the key to understanding matter at its most fundamental level. Neutron stars influence their environment in dramatic ways. In binary systems, where a neutron star orbits another star, the neutron star can strip material off its companion. This material forms a glowing disk that heats up as it spirals inward. When the material finally reaches the star's surface, it can trigger bursts of X-rays so powerful that they flood detectors across Earth. If the neutron star continues feeding, it can spin faster and faster until it becomes a millisecond pulsar, rotating hundreds of times per second. These systems are some of the brightest X-ray sources in the sky. Neutron stars can also collide with each other, and these mergers are some of the most important events in the cosmos. When two neutron stars spiral inward and crash, the collision produces gravitational waves strong enough for detectors on Earth to sense. The energy released in these events is so enormous that it briefly outshines entire galaxies. More importantly, neutron star mergers are responsible for creating many of the heavy elements we find on Earth, including gold and platinum. Every piece of gold in jewelry, electronics, or coins may have been created in the violent collision of two neutron stars billions of years ago. Neutron stars are the universe's most extreme example of what matter can become under pressure. They occupy the narrowest possible space between stability and collapse. Too small to remain normal stars, too large to remain white dwarfs, and too massive to avoid pushing matter into new forms. They are the final stable configuration before gravity becomes overwhelming. Understanding neutron stars is not just about studying collapsed stars. It is about discovering the limits of matter, the boundaries of physics, and the places where the universe reveals what lies beyond our familiar world. Neutron stars may appear simple, small spheres of dense matter rotating silently in space, but every layer of their existence reveals another boundary where normal physics loses its meaning. To understand what makes neutron stars so extraordinary, we have to look not only at how they form, but at the strange rules that govern their behavior afterward. Their existence forces us to rethink what matter is, what gravity can do, and how extreme the universe can become without collapsing into total darkness. These objects are not just remnants of dead stars. They are living demonstrations of nature operating at its most intense limits. The moment a neutron star is born, its environment changes completely. The supernova explosion that created it blasts away the outer layers of the original star, leaving behind a glowing cloud of debris that expands outward for thousands of years. But the neutron star at the center spins rapidly from the very start. The conservation of angular momentum preserves the original rotation of the collapsed core, but because the star has shrunk to a tiny fraction of its size, the rotation speed increases dramatically. This is why newborn neutron stars often rotate dozens of times per second. The intense spin affects everything around them, from their magnetic fields to the radiation they emit. Even at birth, a neutron star behaves more like a high-energy engine than a cooling remnant of a dead star. As the neutron star ages, its rotation gradually slows due to the radiation it emits. But even this slowing happens in an extreme way. The star loses rotational energy through bursts of electromagnetic radiation, particle winds, and magnetic braking. These processes convert the star's rotational energy into powerful beams that sweep across space. The beams create the pulses we detect from pulsars. Remarkably, these pulses are so consistent that even when a neutron star loses energy, it slows in a predictable and steady manner. This predictability is why pulsars are used to test properties of spacetime and gravitational waves. A single neutron star, rotating hundreds of times per second, can act as a cosmic metronome for millions of years without losing its precision. The rotation also affects the shape of the neutron star. Although we imagine them as perfect spheres, neutron stars are not exactly round. Their rapid spin flattens them slightly at the poles and bulges them at the equator. This distortion is small but significant given their extreme density. The star's shape is a delicate balance between centripetal force from rotation and gravitational force pulling inward. A faster spinning neutron star will have a more pronounced bulge. If a neutron star spins too quickly, it can approach the point where the centrifugal force at its equator becomes strong enough to tear it apart. This theoretical limit, called the breakup speed, lies around 1 rotation per millisecond. Some neutron stars have been observed spinning faster than 600 times per second, approaching a large fraction of this limit. They are some of the fastest spinning objects in the universe. The magnetic fields of neutron stars also reveal patterns that shape their evolution. These fields are so intense that they lock the star's rotation and radiation patterns together. The magnetic poles do not always line up with the star's rotation axis. As the star spins, the misaligned poles create sweeping beams of radiation. This misalignment causes the lighthouse effect observed in pulsars. But the magnetic field does more than produce beams. It controls how charged particles move around the star, shapes the structure of the outer atmosphere, and helps regulate the star's cooling. In magnetars, where the magnetic field is thousands of times stronger than that of typical neutron stars, the fields become powerful enough to twist the star's crust. The energy stored in these twisted fields can be released suddenly, producing massive flares that send shockwaves through space. The surface of a neutron star is so extreme that calling it a surface is almost misleading. It is a thin boundary between ordinary physics and matter under unimaginable pressure. The crust is made of tightly packed nuclei arranged in a crystalline structure far stronger than anything on Earth. Below the crust lies a region where neutrons begin to leak out of atomic nuclei, forming a superfluid mixture that behaves in ways nothing on Earth can mimic. This superfluid can move without friction. It can flow through the star's interior like a ghostly liquid. And when it interacts with the crust, it can cause sudden jumps in the star's rotation. These jumps, known as glitches, reveal that the interior of a neutron star is dynamic rather than static. The superfluid stores rotational energy and can release it suddenly, forcing the crust to spin slightly faster. Observing these glitches helps scientists understand the star's internal structure. Deeper inside the star, the density increases to levels where new forms of matter may appear. The behavior of matter under such pressure is one of the great mysteries of physics. Some models suggest the presence of hyperons, particles containing strange quarks. Others suggest that the density is so high that neutrons dissolve into their components, forming a quark-gluon plasma. If true, this would mean that the core of a neutron star contains matter that has not existed since the first moments after the Big Bang. The exact composition of the inner core remains unknown because the pressures involved cannot be replicated in any experiment. Neutron stars are the only natural objects that reach such extreme conditions, which makes them priceless laboratories for studying the fundamental structure of matter. The gravitational field of a neutron star is another realm where reality bends. Standing on the surface, if it were possible, would mean experiencing gravity, hundreds of billions of times stronger than Earth's. Light escaping from the surface is bent significantly. If you looked up from the surface, you would see the sky distorted by gravitational lensing. Colors would shift. Time would slow. The star's gravity is so strong that even photons, the fastest-moving particles in the universe, struggle to escape. This intense gravity plays a major role in shaping the star's environment, affecting how radiation spreads, how particles move, and how the star interacts with surrounding material. Many neutron stars exist in binary systems, meaning they orbit another star. These systems create some of the most dramatic events in the universe. When the neutron star's companion expands during its evolution, it can begin transferring mass to the neutron star. The material forms a disk around the neutron star and slowly spirals inward. As it falls, it heats up to millions of degrees, producing bright X-ray emissions. These X-ray binaries are among the most luminous objects in the galaxy. They show how neutron stars behave when fed a steady stream of matter. In some cases, the matter piles up on the neutron star's surface until it triggers massive nuclear explosions called X-ray bursts. These bursts release enormous amounts of energy in just a few seconds. If a neutron star continues to gain mass, the added weight may push it beyond the limit of stability. Once the neutron degeneracy pressure can no longer hold back gravity, the star collapses further, forming a black hole. This collapse marks the true end of the star's existence as a physical object. It becomes a region where gravity is so strong that not even light can escape. The transition from a neutron star to a black hole is one of the most dramatic transformations in the universe. It shows how narrow the line is between extreme matter and total gravitational domination. Neutron stars do not only collapse, they also collide. When two neutron stars orbit each other, they gradually lose energy in the form of gravitational waves. These waves stretch and compress space itself. As the neutron stars spiral inward, they accelerate, moving faster and faster until they finally merge in a violent collision. This collision produces a burst of gravitational waves strong enough to be detected by Earth-based instruments. It also produces a massive explosion called a kilonova. These explosions create heavy elements, including gold, platinum, and uranium. The metal in jewelry, electronics, and even ancient artifacts may have originated in a neutron star collision billions of years ago. This connection between cosmic events and everyday materials is a reminder of how deeply our world is linked to the universe. The rotation, magnetic fields, and internal structure of neutron stars continue to evolve over time. As the star ages, it cools, slows down, and becomes less active. Some neutron stars eventually stop producing radio pulses and become invisible in most wavelengths. Others remain detectable due to their thermal radiation or their interactions with the surrounding space. Even as they fade, neutron stars remain dense and stable. Their extreme nature does not diminish with time. They become cold embers of collapsed stars, yet they continue to exist as some of the strangest and most powerful remnants in the universe. Understanding neutron stars is not just about studying collapsed stars, it is about exploring the extreme edges of physics, places where matter behaves in ways that defy normal experience. These stars test our theories of gravity, magnetism, and quantum mechanics. They reveal states of matter that cannot exist on Earth, and they challenge our understanding of what the universe allows. The more we learn about neutron stars, the more we realize that they are not simply exotic objects. They are keys to understanding the structure of reality itself. Neutron stars continue to challenge our understanding of reality because everything about them pushes against the limits of the known universe. They compress matter into densities that no ordinary object can reach. They twist magnetic fields into shapes so intense that our technology can barely detect them. They rotate at speeds so fast that physics has to stretch to accommodate the forces involved. And yet, despite all of this, neutron stars are stable. They exist for millions, even billions of years, simply holding themselves together under the enormous pressure of their own gravity. This stability is one of the most astonishing things about them. They are constantly under tension, constantly fighting collapse, constantly balancing on the edge of becoming something even more extreme. But instead of breaking apart or collapsing immediately, they persist. One of the most fascinating aspects of neutron stars is how they interact with their surroundings. Even in isolation, a neutron star exerts a gravitational influence on everything nearby. Its gravity is strong enough to bend the path of light. It is strong enough to alter the orbit of distant objects. And it is strong enough to trap gas clouds and dust in long, curving patterns. But when a neutron star is part of a binary system, its influence becomes even more dramatic. The companion star plays a crucial role in shaping the neutron star's evolution. If the companion is still burning hydrogen, it may not immediately interact with the neutron star. But once it expands into a giant, its outer layers become vulnerable. The neutron star can begin pulling this material inward, forming an accretion disk that heats up to millions of degrees. This disk shines brightly in X-rays, turning the system into a powerful source of radiation. As the neutron star accretes matter, it undergoes changes that affect its rotation, temperature, and magnetic field. The added mass increases its gravitational pressure, slightly squeezing the star further. The angular momentum of the incoming material can spin the neutron star faster, sometimes turning it into a millisecond pulsar. These pulsars rotate so rapidly that a single rotation takes less time than a blink of an eye. The fact that something as massive as a neutron star can rotate hundreds of times per second without flying apart is one of the strongest demonstrations of how extreme neutron matter really is. The pressure inside the star is so high that it can resist the incredible centrifugal force created by this rapid spin. Accretion can also lead to surface explosions. When enough material accumulates on the neutron star's surface, the intense heat and pressure can trigger a thermonuclear runaway event. These explosions, known as Type 1 X-ray bursts, are short but extremely powerful. They release nuclear energy across the surface in a wave that circles the star in seconds. To an outside observer, the star suddenly brightens dramatically before fading back to normal. These bursts show that even though neutron stars are incredibly stable internally, they can still experience violent reactions at their surface when external material accumulates. Some neutron stars go beyond bursts and enter a far more violent phase. They become magnetars. Magnetars are among the rarest and most extreme objects in the universe. Their magnetic fields are so strong that they distort the shape of atoms. These fields can also twist the star's crust. When the crust can no longer support this magnetic stress, it cracks. This cracking releases enormous amounts of energy, producing flares so intense they can temporarily outshine every other source of X-rays in the galaxy. These flares are some of the brightest electromagnetic events ever recorded. One magnetar flare, observed in 2004, was powerful enough to affect Earth's ionosphere, even though the magnetar was located over 50,000 light-years away. This kind of energy output shows how much power is stored in a magnetar's magnetic field, and how unstable that energy can become. Even neutron stars that do not become magnetars often experience internal activity in the form of glitches. These glitches are sudden increases in rotational speed, caused by interactions between the superfluid interior and the solid crust. The superfluid can store rotational energy in quantized vortices, tiny whirlpools that behave according to quantum rules. When these vortices shift or unpin from the crust, they transfer energy suddenly, causing the crust to spin slightly faster. Glitches reveal that the interior of a neutron star is not a single uniform structure, but a layered composition of different states of matter interacting in complex ways. Studying glitches helps scientists map the star's internal behavior, even though the star is thousands of light-years away. Neutron stars also produce some of the most puzzling signals in astronomy. fast radio bursts. These millisecond-long pulses of radio waves come from deep space and release enormous amounts of energy. Some fast radio bursts repeat, while others seem to occur only once. Although the exact cause of these bursts is still debated, magnetars are one of the leading explanations. Their magnetic fields can rearrange suddenly, producing bursts of energy that escape as radio waves. When these bursts travel across billions of light years and still reach Earth strong enough to measure, it shows how incredibly powerful the source must be. This brings us to one of the most important roles neutron stars play in the universe. They are factories of heavy elements. The universe began with mostly hydrogen and helium. Everything heavier had to be created inside stars or during violent cosmic events. Neutron stars, especially when they collide, produce elements heavier than iron. These include gold, platinum, and other rare metals that play essential roles in technology and the world around us. When two neutron stars merge, they eject clouds of neutron-rich matter into space. As this matter expands and cools, it forms new atomic nuclei through rapid neutron capture. The light from these events, called kilonovae, reveals the creation of new elements. This means much of the gold and platinum on Earth originated from ancient neutron star collisions that occurred billions of years before the solar system formed. Neutron star collisions also release gravitational waves, ripples in the fabric of spacetime predicted by Einstein. These waves spread outward at the speed of light, stretching and compressing space itself. When they reach Earth, they cause tiny, measurable distortions. The detection of gravitational waves from a neutron star merger in 2017 marked one of the most significant scientific achievements of the century. For the first time, astronomers observed the same event in gravitational waves and electromagnetic light. This breakthrough opened an entirely new way to study the universe. Neutron stars, with their intense gravity and precise motions, are ideal tools for exploring the nature of space and time. They allow scientists to test relativity in ways impossible on Earth. The future of a neutron star depends largely on its mass and environment. An isolated neutron star may cool over billions of years, gradually losing energy until it becomes almost invisible. A neutron star in a binary system, however, may continue to evolve dramatically. It may gain mass, spin faster, experience bursts, emit jets, or eventually collapse into a black hole. The path each neutron star follows reveals how delicate the balance of forces inside it truly is. Just a slight increase in mass or rotation can push it over the edge, sending it into collapse. Neutron stars also help scientists understand the behavior of matter at nuclear densities. Many theoretical models describe how matter behaves under extreme pressure, but neutron stars provide real examples that can confirm or challenge these models. Observations of neutron star masses, radii, and temperatures help physicists refine their theories of nuclear interactions, superfluidity, and exotic forms of matter. This makes neutron stars essential tools for understanding the physics of the early universe and the behavior of matter at its most fundamental level. Despite all their extreme properties, neutron stars are remarkably common. The Milky Way contains hundreds of millions of them, most of which are old, cold, and nearly invisible. Only a small fraction are active pulsars or magnetars detectable from Earth. This hidden population of neutron stars drifts silently through the galaxy, each one a leftover from the death of a massive star. If you could see them all at once, the Milky Way would be filled with tiny, dense spheres scattered like grains of cosmic metal. They are the fossils of stellar evolution, reminders of the universe's violent past. Neutron stars represent a unique category of objects in the cosmos. They are neither fully alive like main sequence stars, nor fully dead like black holes. They exist in a transitional state, suspended at the boundary between matter and collapse. Their extreme conditions provide insight into forces that operate far beyond ordinary experience. They reveal how gravity shapes matter, how quantum mechanics governs ultra-dense particles, and how magnetic fields behave when stretched to cosmic extremes. They connect the life cycles of stars with the structure of galaxies and the creation of elements that eventually form planets and living beings. In many ways, neutron stars are the universe at its most intense and its most revealing. They show us how small objects can hold unimaginable power, how violent events can create beauty, and how matter can exist in states far outside our intuition. Every neutron star is a monument to the forces of nature working at full strength, compressing a star into a compact core that stands on the edge of what physics allows. And as we continue studying them, neutron stars remain one of the greatest frontiers in understanding the extremes of the cosmos. Neutron stars are some of the smallest objects in the universe, yet almost everything about them acts on the scale of galaxies. Their gravity, their magnetic fields, their rotation, their collisions, all of these forces extend far beyond their physical size. A neutron star is only about 20 kilometers wide, but the influence it has on the space around it can stretch for thousands or even millions of kilometers. This contrast between size and effect is one of the most fascinating things about neutron stars. They serve as reminders that in the universe, size does not determine power. Density, gravity, and energy matter far more. And neutron stars concentrate these properties in ways nothing else in nature can match, except a black hole. One of the most surprising aspects of neutron stars is how they evolve over time. They begin their lives in the chaos of supernova explosions, surrounded by shock waves and debris. Immediately after formation, a newborn neutron star is incredibly hot, with temperatures reaching around 1 trillion degrees Kelvin. At this point, the star glows with intense radiation, but it cools rapidly as neutrinos, nearly massless particles, stream out of the star at incredible rates. In the first few minutes, neutrino emission removes almost all the energy produced during the collapse. These neutrinos carry away more energy than the entire electromagnetic output of the supernova. For a short period, the universe becomes a river of escaping neutrinos, and the neutron star fades from a glowing sphere to a compact, cooling remnant. Over the next thousands of years, the neutron star continues to cool, eventually settling into a stable temperature where thermal radiation escapes more slowly. Even as a cool neutron star, its temperature remains millions of degrees, far hotter than the surface of the Sun. This cooling process reveals how efficiently neutron matter conducts heat. Unlike ordinary matter, which cools slowly due to impurities, neutron matter transfers thermal energy almost perfectly. Heat moves through the star in smooth waves, rising to the surface where it escapes as X-rays. Observing the rate of cooling helps scientists understand the internal structure of the star. Faster cooling may indicate the presence of exotic particles or superfluid behavior deep inside. For many neutron stars, rotation becomes one of their defining features. The spectacular spin rates observed in pulsars reveal how collapse transforms angular momentum. A massive star may rotate only once every few days, but when it collapses, its radius shrinks by a factor of tens of thousands. This shrinking compresses the star's rotation, turning a slow spin into a rapid whirl. A pulsar rotating hundreds of times per second is not unusual. These rotation speeds create enormous centrifugal forces at the equator. Yet the star remains intact because neutron matter is so dense and rigid. The pressure inside supports the star against forces that would tear any normal object apart. This is why neutron stars represent a boundary in physics. They show what matter becomes under pressures so extreme that conventional models fail. The rotation of neutron stars also creates powerful winds. These winds consist of charged particles accelerated by the star's magnetic field. As the star spins, its magnetic field sweeps through space, dragging charged particles along and ejecting them at high speeds. The result is a continuous stream of particles forming a structured wind that can stretch for millions of kilometers. When this wind collides with interstellar gas, it creates glowing nebulae known as pulsar wind nebulae. Some of these nebulae shine brightly in X-rays, revealing the location and power of the central neutron star. The Crab Nebula is one of the most famous examples. At its center lies a pulsar spinning 30 times per second, powering a nebula more than 10 light-years across. The energy driving this vast cloud comes from a star the size of a city. The relationship between neutron stars and their environment becomes even more interesting when we look at how they interact with gas clouds in their vicinity. Neutron stars traveling through space may encounter interstellar gas and dust. Their gravity can bend the flow of this material, creating bow shocks similar to the ripples created by a boat moving through water. If the neutron star has a strong magnetic field, the interaction becomes even more complex. The star's rotation and magnetic pressure can shape the gas into arcs and filaments. These structures are faint, but reveal the motion of the neutron star through space. Observations of these patterns provide valuable information about the star's trajectory, velocity, and magnetic strength. Some neutron stars move incredibly fast. These runaway neutron stars were kicked out of their original location during the supernova explosion that created them. The explosion is not always symmetrical. If one side of the star expels slightly more material than the other, the neutron star receives a recoil kick. Some kicks can exceed 1,000 kilometers per second. This means that a neutron star, only 20 kilometers wide, can travel across the galaxy faster than most spacecraft could ever dream of. These runaway stars streak through space like high-speed bullets. They can cover thousands of light-years in a relatively short time, carrying their magnetic fields and particle winds along with them. Some of these neutron stars eventually leave their home galaxies entirely, drifting into intergalactic space. The interaction between neutron stars and light is another strange phenomenon. The gravity of a neutron star is so strong that it bends light passing near it. This bending is a direct demonstration of general relativity, showing how mass warps the fabric of space-time. For neutron stars with strong magnetic fields, the bending of light becomes even more complex. The magnetic fields can polarize light, altering its direction and intensity. Observing neutron star light reveals subtle patterns that help scientists measure magnetic strength and gravitational curvature. These measurements turn neutron stars into natural laboratories for testing the limits of relativity and quantum physics. One of the most fascinating discoveries about neutron stars is that some of them emit jets of material. These jets occur when a neutron star is accreting matter from a companion. As the material spirals inward, it forms a disk that can twist the magnetic field. This twisting creates channels where particles are accelerated outward at nearly the speed of light. These jets can stretch for thousands of kilometers and emit X-rays and gamma rays. Jets are more commonly associated with black holes, but neutron stars can produce them too. The presence of jets shows that even though neutron stars are not singularities, their magnetic and gravitational systems are powerful enough to mimic some black hole behaviors. Neutron stars also help shape the chemical evolution of galaxies. Because they produce heavy elements during collisions, they contribute to the enrichment of interstellar gas. This enriched gas forms new stars and planets. Every neutron star collision sends waves of precious metals into space, seeding future solar systems with the elements needed for planets, atmospheres, and complex chemistry. Without neutron stars, the universe would be far poorer in the elements required for life. Gold, platinum, and other heavy elements would be rare traces instead of familiar materials. The connection between neutron stars and planetary formation shows how deeply cosmic events influence the structure of the universe. Some neutron stars exist in systems with two neutron stars orbiting each other. These binary neutron star systems are among the most important objects in astronomy. Their orbits decay due to gravitational wave emission, causing them to spiral inward slowly. Over millions of years, their orbit tightens until they collide. The collision releases gravitational waves, gamma-ray bursts, and heavy element-rich ejecta. Observing these collisions gives scientists direct insight into how matter behaves under the most extreme conditions. The 2017 neutron star merger was a groundbreaking moment in science because it provided the first multi-messenger observation of such an event. Scientists detected gravitational waves, gamma rays, X-rays, optical light, and radio waves from the same source. This confirmed theories about kilonova explosions and heavy element formation. It also demonstrated how neutron stars serve as laboratories for understanding fundamental physics. Even isolated neutron stars, which do not accrete matter or produce bursts, offer valuable insights. Their cooling rates reveal their internal structures. Their motion across the sky reveals their birth velocities. Their magnetic fields reveal the evolution of stellar remnants. Some neutron stars show faint optical or ultraviolet emissions that help scientists measure their surface composition. Others emit soft X-rays that reveal their temperature. Each neutron star, even a quiet one, is a treasure of information about how matter behaves at nuclear density. The final fate of neutron stars depends on their mass and environment. A neutron star may remain stable for billions of years, slowly cooling and fading until it becomes nearly invisible. If it gains enough mass from a companion, it may collapse into a black hole. If it collides with another neutron star, it may be destroyed in a burst of heavy element production. Some neutron stars may even drift into intergalactic space, forever isolated from anything that could change their structure. No matter how they end, neutron stars leave a profound impact on the universe. They are reminders of the power of gravity, the limits of matter, and the strange beauty of the cosmos at its most extreme. Neutron stars push physics to its breaking point. They exist at the boundary between matter and collapse. They show us what happens when nature compresses atoms into a structure so dense that familiar rules disappear. They reveal how stars live, die, and transform into objects far more exotic than anything imagined in everyday experience. They hold clues to the behavior of particles, the structure of space-time, and the forces that shaped the early universe. And as we continue studying them, neutron stars remain some of the most mysterious and awe-inspiring objects ever discovered. Neutron stars sit at the crossroads of many of the universe's most intense processes, and understanding them requires thinking in scales that go far beyond everyday experience. Everything about them is extreme. The pressure inside their cores, the speed at which they spin, the density of their matter, the strength of their magnetic fields, the energy of their flares, and the violence of their collisions. Yet the more scientists study them, the more neutron stars reveal how surprisingly organized and stable these extremes can be. A neutron star is not chaotic in the way a supernova is. It is stable in its extremity, balanced in a way that seems impossible. It is the universe's way of showing that even the most violent collapse can produce something remarkably structured. To appreciate neutron stars fully, it helps to understand how they behave not just as isolated objects, but also as engines of change in the regions around them. A neutron star's environment evolves continuously. After the chaos of the supernova fades, the space around the neutron star becomes a laboratory shaped by gravity, radiation, and magnetic fields. If the neutron star is young, the surrounding nebula still glows with the expanding debris. This debris may interact with the neutron star's wind, forming complex patterns of light and gas. These structures tell the story of how the star formed and how its energy spreads through space. As the debris disperses over thousands of years, the neutron star remains, spinning steadily and cooling slowly, a stable object amid the fading aftermath of stellar death. The magnetic field plays a major role in shaping this environment. Most neutron stars possess incredibly strong magnetic fields from the moment they form, because their original star's magnetic field becomes compressed along with everything else during collapse. This compression increases the magnetic strength by trillions of times. The magnetic field influences how charged particles move near the star, creating radiation belts, twisting field lines, and accelerating particles to enormous speeds. In some neutron stars, the magnetic field remains stable for millions of years. In others, especially magnetars, the field becomes unstable and begins to shift. These shifts can generate enormous stress on the star's crust. When the crust cracks under this stress, the sudden release of energy produces flares that echo across the galaxy. A magnetar flare is one of the most dramatic events neutron stars can produce. These flares occur when the magnetic field rearranges itself suddenly, releasing a burst of energy that travels outward in the form of gamma rays and X-rays. The energy involved is immense. In a fraction of a second, a magnetar can release as much energy as the sun produces in thousands of years. These flares can ionize material thousands of kilometers away, distort Earth's magnetic field, and saturate detectors designed to measure cosmic radiation. A single magnetar flare detected in 2004 was so powerful that it briefly overwhelmed instruments across space and on the ground, despite coming from a star thousands of light years away. The fact that such a small star can release this much energy shows how extreme magnetic fields become when compressed into such a dense object. Yet neutron stars also display remarkable stability. Pulsars, for example, maintain astonishing precision in their rotation. Some pulsars are so predictable that they function as natural timekeepers. Scientists use them to measure changes in the galaxy, detect gravitational waves, and refine models of cosmic behavior. These pulsars emit beams of radiation that sweep across space as the star rotates. Each pulse arrives at Earth with a regularity that rivals atomic clocks. This precision is one of the most surprising features of neutron stars. Despite the violent forces acting inside them, despite the intense gravity and the warped space-time around them, they behave in ways that are orderly and predictable. But neutron stars are not immune to change. Over time, their rotation slows. This slowdown is caused by the loss of rotational energy through radiation and particle winds. As the star loses energy, its pulses stretch slightly. The star's magnetic field also evolves. Many neutron stars begin with strong magnetic fields that gradually weaken over millions of years. The weakening of the magnetic field reduces the star's ability to produce powerful beams and particle winds. Eventually, the pulses may fade entirely as the star becomes too weak to emit detectable radiation. These aging neutron stars become quiet, nearly invisible objects drifting through space. Their presence can only be inferred from subtle gravitational effects or faint thermal emissions. Some neutron stars, however, undergo sudden changes that disrupt their regular behavior. Glitches are a prime example. These sudden jumps in rotational speed reveal that the interior of the star is not a rigid body, but a complex system of layers. The superfluid interior stores rotational energy in quantized vortices, and these vortices can become pinned to the crust. When they unpin, they release stored energy suddenly, causing the star to spin faster. Glitches show that the interior of a neutron star behaves in ways no ordinary fluid does. They offer a glimpse into the quantum mechanical behavior of matter at extraordinary densities, far beyond anything achievable in a laboratory. Another remarkable behavior comes from neutron stars in binary systems. Binary neutron stars experience intense tidal forces that alter their rotation and energy output. As they orbit each other, their mutual gravity stretches and compresses their surfaces. These tidal interactions can heat the stars, accelerate their spin, and trigger bursts of radiation. Over time, these interactions drain orbital energy from the system. The neutron stars spiral closer together, moving faster as they approach. The final stages of the merger happen quickly. The stars orbit each other dozens of times per second, releasing gravitational waves that ripple through the universe. When they collide, the impact produces a kilonova, a massive explosion that spreads newly formed heavy elements across space. These mergers are among the most important events for building the chemical complexity of galaxies. The gravitational waves produced during these mergers tell us about the internal structure of neutron stars. As the stars spiral inward, they deform slightly due to tidal forces. These deformations alter the gravitational wave signal, providing information about the stiffness of neutron matter. By analyzing these signals, scientists can estimate the star's radius, mass distribution, and possible composition. This is one of the only ways to study the internal behavior of neutron stars directly. The gravitational wave signals act as fingerprints of the star's internal physics, revealing how matter behaves under pressures so high that neutrons themselves become compressed. Some neutron stars take on unusual forms as they evolve. For example, accreting neutron stars, those absorbing material from a companion, can build up layers of lighter elements on their surface. These layers behave strangely under extreme pressure. Some layers ignite in nuclear fusion bursts that spread across the surface. Others undergo slow-burning reactions that gradually change the star's appearance. Accreting neutron stars can also emit jets of material that shoot into space at nearly the speed of light. These jets are shaped by the star's magnetic field and can extend for thousands of kilometers. They emit X-rays and gamma rays and often vary in brightness as the accretion rates change. Neutron stars may also possess mountains, tiny bumps on their surface only centimeters tall, but huge by neutron star standards. These mountains create slight asymmetries in the star's shape, which can produce continuous gravitational waves as the star rotates. Observing these waves would provide even more information about the star's interior. The existence of such mountains shows that even slight deviations from perfect symmetry can have enormous consequences for how neutron stars emit energy. The interaction between neutron stars and nearby objects reveals more about their behavior. Neutron stars with planetary systems, although rare, have been discovered. These planets orbit in stable configurations, surviving despite the star's violent past. Their existence suggests that either the planets formed after the supernova, or they are remnants from a disrupted system that settled into new orbits. Studying these planets provides insight into how planetary systems can survive catastrophic events. Neutron stars also interact with space-time in ways that reveal the nature of gravity itself. For example, binary pulsars provide tests of general relativity. Their orbits decay at rates predicted by Einstein's equations when accounting for energy lost through gravitational waves. These observations were among the earliest confirmations of gravitational wave theory long before detectors existed. Neutron stars continue to serve as natural experiments in strong gravity, allowing scientists to test relativity under conditions that cannot be replicated anywhere else. The long-term evolution of neutron stars shows how they remain dynamic even after their most violent stages have passed. Over millions of years, their magnetic fields weaken, their rotation slows, and their temperature decreases. But even as they fade, neutron stars remain some of the universe's most interesting objects. They remember the forces that created them. Their interior structures preserve information about the early universe. Their collisions create elements that form planets and life. Their gravitational waves carry signatures that reveal the structure of matter itself. Neutron stars stand at the boundary of what the universe allows. They are the last stable form before collapse becomes complete. They represent the limits of density, the extremes of magnetic power, the fastest rotations matter can survive, and the deepest tests of gravity's strength. They are remnants of stellar death, but they also shape the future of galaxies. Each neutron star carries a history of collapse, survival, and transformation. And throughout the universe, millions of them continue to shine, rotate, collide, and drift. Each one a reminder that the cosmos is far more extreme and far more complex than anything we experience on Earth. As we look deeper into the universe, neutron stars continue revealing behaviors that push the limits of what we understand. They are some of the smallest objects we can observe directly, yet they behave on scales typically reserved for entire galaxies. They can emit more power in a burst than the sun produces in 100,000 years. They can accelerate particles to near light speed. They can warp space-time. They can survive impacts, flares, and gravitational forces that would tear any other object apart. And even though they often appear quiet and distant, neutron stars are constantly active internally, constantly shaping their environment and constantly holding themselves together against pressures so extreme that matter reaches its breaking point. One of the strangest aspects of neutron stars is the way they challenge our ideas about what matter is physically capable of. Inside a neutron star, atoms do not exist. Their structure collapses. Electrons merge with protons. Neutrons pack into a state where the distances between particles are smaller than anything in nature except inside atomic nuclei. This makes the entire star behave like one giant atomic nucleus. But with properties far beyond anything nuclear, physics encounters under normal conditions. The pressure is so immense that even the neutrons themselves may begin to break down into their components. This possibility of quark matter is one of the biggest mysteries surrounding neutron stars. If quark matter does exist in their cores, neutron stars would become the only place in the universe where the early conditions of the Big Bang remain frozen inside a stable object. They may carry within them the same type of matter that existed microseconds after the universe began. This idea becomes even more compelling when we consider that neutron stars are not uniform on the inside. Their density changes from the surface to the core. The outer crust is rigid, crystalline, and incredibly strong. Beneath that crust, matter becomes so dense that neutrons begin to drip out of nuclei, forming a fluid that permeates the inner layers. This neutron fluid behaves differently from anything we have on Earth. It is a superfluid, meaning it flows without friction. This superfluidity explains why neutron stars can maintain stable rotation for millions of years, and why they experience sudden glitches. When the superfluid interior decouples from the crust suddenly speeds up, creating the small but measurable rotational jumps that scientists detect. These glitches are like earthquakes deep inside the star, caused not by shifting tectonic plates, but by quantum mechanical effects happening at nuclear densities. The crust itself contains structures known as nuclear pasta, exotic arrangements of nuclear material shaped by competing forces. These structures have names like lasagna, spaghetti, and gnocchi, not because they resemble food, but because their shapes resemble sheets, strands, and clusters of nuclear particles. Nuclear pasta may be one of the strongest materials in the universe, capable of withstanding stresses that would shatter any normal material. The existence of nuclear pasta shows how neutron stars push matter into forms that never occur naturally elsewhere. These structures arise simply because the density becomes so high that ordinary nuclear shapes are no longer stable. Matter stretches, twists, and reorganizes into new configurations under the star's gravitational pressure. The surface of a neutron star offers another layer of extreme physics. Even though the crust is only centimeters thick, it carries the full weight of the star's immense gravity. Standing on a neutron star's surface would be impossible. A person would be flattened instantly by gravitational forces billions of times stronger than anything experienced on Earth. A pebble dropped from 1 meter above the surface would strike with the energy of a nuclear explosion. If you could observe the surface directly, you would see a glowing, turbulent world where heat leaks out slowly over millions of years. The light escaping from the surface is bent by gravity, making the star appear slightly larger than it truly is. This gravitational bending allows us to see areas of the star that would normally be hidden behind its horizon. Because of their high temperature, neutron stars emit thermal X-rays, especially when they are young. These X-rays help scientists measure the star's surface temperature and confirm that cooling happens slowly over time. Older neutron stars emit less thermal radiation, but may still be visible due to their magnetic fields or interactions with nearby material. Even after billions of years, when they have cooled significantly, neutron stars remain far hotter than any normal rock or planet could ever be at the same age. Their heat is a leftover from the violent collapse that created them. Neutron stars become even more interesting when they exist in binary systems. A neutron star with a massive companion can engage in dramatic, ongoing interactions. As the companion evolves and expands, it may begin transferring mass to the neutron star. This mass transfer has multiple effects. The neutron star gains mass, which brings it closer to the threshold of collapsing into a black hole. The angular momentum of the infalling material spins the neutron star faster, potentially turning it into a millisecond pulsar. The material also heats up as it falls, producing intense X-ray emissions. These interactions can continue for millions of years, transforming the neutron star and altering the orbit of the binary system. Eventually, the companion star may lose so much mass that it becomes a white dwarf, or, in some cases, another neutron star. Binary neutron stars that contain two neutron stars orbiting each other are some of the most valuable objects in astronomy. Their gravitational interactions are so intense that they slowly spiral inward. The loss of orbital energy through gravitational waves causes their orbit to shrink. As they draw closer, their orbital speed increases dramatically. During the final moments before they merge, the two neutron stars orbit each other many times per second. This rapid motion distorts space-time in predictable patterns that detectors like LIGO and Virgo can measure. The measurement of gravitational waves from neutron star mergers marked a turning point in astronomy. For the first time, scientists could listen to the universe instead of simply looking at it. When neutron stars merge, the force of the collision is unimaginable. The two stars crash into each other with such energy that they release gamma-ray bursts, gravitational waves, and heavy elements all at once. The resulting explosion, called a kilonova, glows in multiple wavelengths: visible light, ultraviolet, infrared, X-ray, and evolves quickly over days to weeks. These kilonova events confirm that neutron star collisions are responsible for creating many of the heaviest elements in the universe. This means that the gold in jewelry, electronics, and ancient artifacts likely originated from collisions between neutron stars billions of years ago. Every heavy atom is a fossil of a cosmic explosion so powerful that it reshaped the chemistry of entire galaxies. Neutron stars are also key to understanding the large-scale behavior of galaxies. Their supernova origins enrich galaxies with heavy elements. Their pulsars provide precise timing signals that help map the structure of the Milky Way. Their collisions distribute rare metals that contribute to the formation of planets, moons, and potentially life. Neutron stars may be small in size, but their influence touches almost every aspect of cosmic evolution. They act as engines that recycle material from dead stars into new generations of stars and planets. But neutron stars also remind us of the universe's violence. They are born through destruction. They evolve through intense forces. They die in collisions or collapse into black holes. Their existence is a constant balance between stability and collapse, between quantum pressure and gravitational pull. They show how thin the boundary is between matter and energy, between structure and chaos, between existence and disappearance. Neutron stars sit on that boundary for millions or billions of years, maintaining their form until something pushes them beyond their limits. Despite their extreme nature, neutron stars can be surprisingly hard to detect. Many of them are old, cold, and quiet. They emit little radiation. They drift through space almost invisibly. The Milky Way contains hundreds of millions of neutron stars, yet we have detected only a small fraction. Most remain hidden, their presence marked only by subtle gravitational effects. Some neutron stars may be wandering through interstellar space completely alone, without any nearby material to reveal their existence. These isolated neutron stars are like cosmic ghosts, survivors of ancient explosions, drifting silently through the darkness. Even the neutron stars we can observe continue to hold mysteries. Some emit unusual bursts of energy. Some pulse irregularly. Some have magnetic fields so strong that they defy theoretical limits. Some exhibit rotational patterns that suggest new forms of matter inside. Each neutron star behaves like a puzzle piece that helps build a larger picture of how matter behaves under extreme pressure. Studying them pushes physics forward. It reveals new possibilities about the structure of the universe, the behavior of particles, and the forces that govern cosmic evolution. Neutron stars are not just remnants of stellar death. They are some of the most important objects in the universe. They show us how stars end, how elements form, how gravity shapes matter, how space-time behaves under pressure, and how galaxies evolve over billions of years. They hold answers to questions about the early universe, the nature of matter, and the limits of physical laws. And even though they are small, their story stretches across cosmic time and reaches into every corner of the universe. The deeper we explore neutron stars, the clearer it becomes that they are not just extreme remnants of stellar collapse. They are systems where multiple physical forces reach their limits simultaneously. Gravity, quantum mechanics, relativity, magnetism, nuclear physics, and particle behavior all collide inside these tiny spheres. They are built from extremes, sustained by extremes, and they express themselves through extremes. Everything they do pushes the universe to reveal the boundaries of what is possible. And as scientists continue studying them, neutron stars remain one of the most important keys to unlocking the deeper structure of reality. One of the most fascinating features of neutron stars is their ability to transform energy in a way no other object can. The energy stored in their rotation alone can power entire nebulae. A neutron star rotating hundreds of times per second carries unimaginable angular momentum. This rotation drives powerful winds that ripple out into space. It fuels magnetic activity. It shapes the surrounding nebula into swirling structures of light and gas. Over time, the neutron star slowly loses this rotational energy, spreading it across the cosmos. Even as it slows, the energy it releases influences everything from nearby gas clouds to the dynamics of binary systems. Rotation also affects how neutron stars cool. A rapidly spinning neutron star radiates energy more efficiently than a slower one. The faster movement intensifies magnetic interactions and particle winds, creating additional pathways for energy loss. But cooling is not just an external process. Inside the star, temperature and density evolve together. The superfluid interior plays a major role in heat transfer. Because superfluids conduct heat extremely well, the temperature inside a neutron star remains surprisingly uniform. This uniformity allows scientists to model cooling curves that reveal the presence of exotic particles or superfluid phases. The cooling history of a neutron star acts like a timeline of its internal evolution, revealing changes that are otherwise invisible. Some neutron stars cool far faster than expected. When this happens, it suggests that a new state of matter may have formed in their core. The appearance of particles like hyperons or the transition to quark matter could create conditions where neutrinos escape more easily, accelerating the cooling process. Observing these rapid cooldowns gives researchers a rare view into the behavior of matter at densities that exceed the capabilities of any experiment on Earth. These observations help refine nuclear models, test theories of superfluidity, and explore scenarios where neutrons dissolve into their component quarks. The behavior of neutron stars in binary systems continues to reveal new extremes. When a neutron star orbits a white dwarf, or another neutron star, the tidal forces between them become significant. These tidal forces distort the shape of the neutron star slightly, affecting its rotation and internal structure. The distortions also influence the emission of gravitational waves. The closer the star's orbit, the more intense these interactions become. As the orbit decays, the star's tidal effects increase dramatically, especially in the moments leading up to a merger. These tidal interactions stretch and squeeze the neutron stars in ways that alter their internal configuration. The resulting gravitational waves carry imprints of these deformations, offering a unique opportunity to study the star's interior indirectly. The merger itself is one of the most violent processes the universe produces. Two neutron stars colliding release energy in multiple channels: gravitational waves, electromagnetic radiation, particle ejections, and thermal emissions. The collision produces a hot, dense remnant that may briefly form a hypermassive neutron star, a star so massive that it sits right at the edge of stability. This object survives for only milliseconds before collapsing into a black hole. During that brief moment, it becomes the densest object in the universe that is not yet a black hole. The physics inside this hypermassive object is unknown. The pressures and temperatures involved exceed anything that exists elsewhere in the universe. These transient stars are windows into matter at its most extreme state. As the merger settles, a massive amount of material is ejected into space. This material expands, cools, and forms new elements. Heavy elements like gold, platinum, and uranium are created in these moments through rapid neutron capture. The brightness of the kilonova that follows reveals the formation of these elements. Observations show colors shifting from blue to red as the heavy elements absorb photons. These signatures confirm that neutron star mergers are the primary source of heavy elements in the universe. This means that planets like Earth and life itself depend on the extreme physics of merging neutron stars. Every atom heavier than iron in our bodies likely originated in the violent collision of two stars long before the solar system existed. But neutron stars also show that not all cosmic violence is destructive. Their existence allows galaxies to evolve, elements to form, and space to remain dynamic. Their energy output powers nebulae. Their wind influences star formation. Their gravitational pull shapes binary systems. Their remnants enrich galaxies with complexity. Even their quiet phases, where they emit only faint thermal radiation, demonstrate the stability of extreme matter over long time scales. Some neutron stars emit signals that challenge our understanding. Fast radio bursts, for example, may originate from highly magnetized neutron stars. These bursts last only milliseconds, yet they release more energy than the sun emits in days or weeks. Some fast radio bursts repeat, while others do not. Their exact origin is still debated, but magnetars are strong candidates. They have the magnetic power needed to create such bursts. They experience crustal cracking events that can release energy rapidly. They exist in environments where high-energy plasma can generate radio waves efficiently. Observing these bursts helps scientists understand the magnetic behavior of neutron stars and the conditions surrounding them. Other neutron stars emit X-ray pulses that do not match typical pulsar patterns. These stars may have unusual magnetic field configurations, or they may be rotating at rates that produce non-standard pulses. Their signals reveal the diversity of neutron star behavior. No two neutron stars are exactly alike. Their masses differ. Their magnetic fields vary. Their rotational speeds change. Their ages, environments, and histories shape their behavior. This diversity makes neutron stars some of the most complex and informative objects in the cosmos. Even neutron stars that appear quiet from the outside hide enormous internal activity. Their interiors maintain high pressure, strong forces, and complex interactions between particles. Neutrons in the core behave as a superfluid. Protons form superconducting phases. Vortices move through the interior in quantized patterns. These internal motions influence the star's magnetic field, cooling rate, and even its rotational glitches. Studying these processes helps scientists understand quantum behavior on macroscopic scales. Neutron stars are one of the few places in the universe where quantum mechanics and relativity operate simultaneously at full strength. The gravitational field of a neutron star also affects the space around it in subtle ways. Light passing near a neutron star bends strongly, revealing the curvature of space-time. Particles moving near the star accelerate rapidly, gaining energy they could never achieve under normal conditions. Observations of neutron starlight reveal gravitational redshift, light losing energy as it climbs out of the star's deep gravitational well. This effect provides direct evidence of general relativity operating in extreme conditions. Measuring the redshift helps scientists estimate the mass and radius of neutron stars, offering clues about their internal structure. Neutron stars also influence the motion of stars in their vicinity. In dense star clusters, a neutron star's gravity can affect nearby orbits. Some neutron stars may capture passing stars or planets. These captures create unusual binary systems or planetary systems in unexpected places. The fact that neutron stars can host planets shows how resilient planetary formation can be. Even after a supernova explosion, conditions may still allow new structures to form around the surviving remnant. Despite their incredible density and power, neutron stars are fragile in a gravitational sense. A slight increase in mass can push them past the limit of stability. If enough matter accumulates, the star can no longer support itself. The neutrons collapse, and the star becomes a black hole. This transition is irreversible. Once the star crosses that threshold, its identity disappears into a singularity. It no longer behaves like matter. It becomes pure gravitational collapse. This boundary marks the end of neutron star physics and the beginning of black hole physics. In many ways, neutron stars are cosmic storytellers. They record the lives of the stars that formed them. They preserve information about the collapse that created them. They store clues about the early universe in their dense cores. Their signals travel across the galaxy, carrying their stories to distant observers. Each rotation, each pulse, each flare, and each burst reveals something about the structure of matter and the behavior of the universe. Neutron stars are reminders that the cosmos operates on scales far beyond anything we experience on Earth. They show that matter can be crushed until it reaches a state where space-time bends visibly. They show that magnetic fields can grow strong enough to break atoms. They show that energy can emerge from compact objects in explosive bursts. They show that gravity can twist the fabric of the universe into waves that travel billions of light-years. Above all, neutron stars show that the universe is full of extremes, and that those extremes are essential to its evolution. Without neutron stars, galaxies would lack heavy elements. Without their signals, we would not understand many aspects of relativity. Without their collisions, we would not detect gravitational waves. Without their existence, the universe would be quieter, simpler, and far less interesting. As we continue exploring neutron stars, one thing becomes clear. Even though they are tiny on cosmic scales, they dominate their surroundings with an authority that other stars simply cannot match. Their gravity pulls in material with overwhelming force. Their magnetic fields stretch across light years. Their radiation shapes entire nebulae. Their collisions seed galaxies with rare metals, and their pulses become cosmic clocks that keep time across the universe. Every neutron star is more than a collapsed core. It is a machine built from the most extreme conditions nature can produce. It does not fade quietly into space. It continues to influence everything around it long after its parent star has died. One of the most intriguing questions about neutron stars is how they evolve over incredibly long periods of time. We often think of stars as static, slow-changing objects that remain stable for billions of years. But neutron stars are different. Their evolution happens on multiple overlapping timescales. Some processes occur in milliseconds, others take millions of years. Rotation slows gradually, but can be interrupted by sudden glitches. Magnetic fields weaken over millions of years, but can flare violently without warning. Their crust may remain stable for millennia before cracking. Their temperature cools predictably until internal reactions or accretion events heat them again. Every neutron star is like a layered clock with many gears turning at different speeds. The slowing of a neutron star's rotation is one of the most straightforward evolutionary processes. As the star emits radiation and particle winds, it loses rotational energy. Over time, this causes the pulsar's period to increase. A pulsar that once rotated hundreds of times per second may eventually slow to only a few rotations per second. The relationship between rotation speed and age is so consistent that scientists can estimate the age of a neutron star by measuring its spin-down rate. This pulsar age provides clues about the star's history and the supernova that created it. But rotation does not always follow a smooth curve. Glitches interrupt this slow evolution in unpredictable ways. A glitch is a sudden jump in rotation speed caused by a transfer of angular momentum from the superfluid interior to the crust. These events reveal that the interior of a neutron star is constantly active, storing and releasing energy in quantum mechanical ways. Temperature evolution is another major aspect of neutron star aging. Immediately after formation, a neutron star cools rapidly through neutrino emission. This neutrino cooling phase lasts for about 100 years. After that, the cooling slows dramatically. The thermal radiation emitted from the surface becomes the star's primary way of losing heat. Observing old neutron stars helps scientists understand this long-term cooling behavior. Some neutron stars cool faster than predicted, suggesting new forms of matter inside. Others cool more slowly, suggesting different compositions or superfluid arrangements. Cooling curves provide indirect evidence of the conditions deep inside the star, where no direct observation is possible. Magnetic evolution is equally complex. Most neutron stars begin with strong magnetic fields, but these fields weaken over time. This decay happens through processes like ohmic dissipation, Hall drift, and changes in the star's crustal structure. For typical pulsars, this decay happens slowly over millions of years. For magnetars, the decay can be much faster. The rapid decay of a magnetar's magnetic field releases enormous amounts of energy, powering its flares and bursts. When the magnetic field decays enough, the magnetar becomes quieter and eventually behaves more like a typical neutron star. This evolutionary path from magnetar to normal pulsar shows how interconnected magnetic and structural processes are inside these stars. In some neutron stars, the magnetic field does not simply weaken, it rearranges. This rearrangement can twist the crust, creating enormous stress. When the stress becomes too great, the crust cracks. These crustal fractures produce sudden releases of energy, sending shockwaves of radiation into space. The scale of these events is staggering. A small crack in the crust of a magnetar can release more energy than the Sun emits in months. These cracks demonstrate how even minor adjustments in the star's magnetic structure can have dramatic consequences. But neutron stars are not only shaped by internal forces. External interactions play an equally important role in their long-term evolution. A neutron star traveling through the galaxy interacts with interstellar gas and dust. Although neutron stars are small, their gravitational presence can create long bow shocks in the gas ahead of them. These bow shocks form when the star's high velocity compresses the gas into a glowing arc. Some bow shocks shine brightly in infrared light, revealing the path of the neutron star through space. Observing these arcs helps identify runaway neutron stars, those that received violent kicks during their supernova birth and now race through the galaxy at hundreds of kilometers per second. When a neutron star has a binary companion, its evolution becomes even more dramatic. Mass transfer from the companion can spin the neutron star up significantly. This process, called recycling, can transform an old, slow neutron star into a fast-spinning millisecond pulsar. These pulsars rotate so rapidly that their stability becomes a miracle of physics. A star with more mass than the Sun rotates hundreds of times per second and remains intact. This transformation cannot happen to isolated neutron stars. It only occurs when a companion star feeds material into the neutron star's magnetic field, gradually accelerating its rotation. Binary evolution can also produce unusual combinations. For example, some systems contain a neutron star and a white dwarf. Others contain two neutron stars. A few contain neutron stars and black holes. Each combination produces unique interactions. A neutron star orbiting a black hole experiences tidal forces that are far stronger than anything seen in ordinary binaries. These systems distort space-time so intensely that gravitational waves become a dominant form of energy loss. Detecting these systems provides rare opportunities to test general relativity in extreme environments. The most spectacular binary evolution results in neutron star mergers. As the stars spiral toward each other, they emit gravitational waves with increasing intensity. These waves carry information about the star's masses, radii, and internal structures. The final seconds before the collision are chaotic. The stars deform under tidal stress. Their magnetic fields interact. Their interior fluids shift violently. When they finally collide, the energy released spreads across the universe. The resulting kilonova shines brightly for days or weeks as heavy elements form and decay. These mergers produce detectable signals in gravitational waves, gamma rays, X-rays, optical light, and radio waves. They are among the most important events for understanding how the universe builds complexity. But neutron stars also evolve through quieter processes. Isolated neutron stars spend millions of years cooling, slowing down, and drifting through the galaxy. Their magnetic fields fade, their pulses grow weaker. Eventually, they become nearly invisible. These old neutron stars form a hidden population that outnumbers the active pulsars by a wide margin. Many of them drift silently between stars, detectable only through the gravitational lensing they produce or through rare interactions with passing gas. They are relics of ancient stellar deaths, carrying memories of supernova explosions that occurred long before humans existed. Neutron stars may also undergo structural evolution deep within their cores. Over long timescales, Increasing pressure may trigger the formation of new particles or the rearrangement of quark matter. These changes could produce subtle shifts in the star's behavior, such as new glitch patterns, changes in cooling rates, or unexpected bursts of radiation. Because neutron stars operate under pressures far higher than anything achievable on Earth, they remain the only natural laboratories for studying these exotic states of matter. Every observation provides new data that helps refine theories about fundamental physics. Their place in the galaxy also evolves. Neutron stars are born in star-forming regions, but as they age, they drift away. Over millions of years, they spread throughout the galaxy. Some remain in the spiral arms where they were born. Others drift into the galactic halo. Some even escape the galaxy entirely, propelled by supernova kicks. These high-velocity neutron stars travel into intergalactic space, carrying with them the remnants of stars long extinguished. Their relationship with black holes is another fascinating evolutionary path. A neutron star that gains too much mass cannot remain stable. If it accretes enough material from a binary companion or merges with another neutron star, it may cross the maximum mass limit. Once this happens, no force can support it against gravitational collapse. The star becomes a black hole in a fraction of a second. This collapse marks the end of neutron star physics. It becomes a singularity hidden behind an event horizon. This transformation is dramatic and irreversible. But even after collapsing, the remnant influences the galaxy through gravitational waves, energy outputs, and the heavy elements left behind from its merger. Neutron stars represent one of the most extreme outcomes of stellar evolution. But their evolution does not end at formation. They continue to change, respond to forces, release energy, and shape the environment around them. They endure internal rearrangements, external interactions, and cosmic collisions. They exist on a knife edge between stability and collapse. They challenge our understanding of matter, energy, and space-time. And they act as cosmic engines that enrich galaxies with heavy elements and powerful signals. The story of neutron stars is not just about their formation or their collisions. It is about their entire life cycle. From violent birth to long-term evolution, from rapid rotation to slow fade, from powerful magnetic activity to quiet cooling. Their lives span extremes of physics that no other objects experience in the same way. They remain some of the most intriguing and informative remnants in the universe, constantly pushing the boundaries of what we know. The more we explore neutron stars, the more they reveal themselves as crossroads where the universe's greatest forces intersect. They are formed by gravitational collapse, powered by nuclear remnants, shaped by magnetic fields, cooled by neutrinos, stabilized by quantum principles, and eventually destroyed by collisions or accretion. Few objects combine so many extremes in a single form. A neutron star is not simply a dense remnant. It is a working system where gravity, quantum mechanics, relativity, and magnetism all operate at their highest levels. Every behavior they show, every pulse, rotation, flare, burst, and collision is a product of forces that only exist when matter is crushed into its most extreme state. And as we examine them more closely, neutron stars show that even the universe's harshest environments contain intricate order and remarkable stability. One of the most powerful demonstrations of this order is the precision of pulsars. These rotating neutron stars act as cosmic lighthouses that flash beams of radiation at perfectly regular intervals. Some pulsars maintain timing precision so high that they rival the best atomic clocks ever built. This reliability makes them valuable tools for measuring distortions in space-time. By monitoring tiny variations in pulsar timing, scientists can detect gravitational waves that ripple through the galaxy. These waves stretch and compress space itself, altering the arrival time of pulsar signals by fractions of microseconds. By analyzing these subtle changes, scientists can map large-scale cosmic events that occurred thousands or even millions of light-years away. Pulsars therefore act as natural detectors spread across the galaxy, helping us observe phenomena far beyond the reach of telescopes. But pulsars are not perfect. Their internal structure occasionally disrupts their precision. Glitches, those sudden jumps in rotation speed, reveal the deep complexity of neutron star interiors. A glitch occurs when the superfluid neutrons inside the star suddenly transfer angular momentum to the crust. This process must overcome forces stronger than anything found in normal matter. It is a quantum mechanical event happening on a macroscopic scale. These glitches create valuable opportunities for understanding how superfluids behave under extreme conditions. While laboratories on Earth can study superfluids made of helium or other light atoms, nothing on Earth can reproduce a superfluid that exists under the pressures found inside a neutron star. Every glitch is therefore a glimpse into a state of matter that exists nowhere else in the universe. Even more mysterious than glitches are the bursts and flares emitted by magnetars. These powerful neutron stars occasionally produce eruptions so violent that they saturate detectors across the solar system. The energy released in a magnetar flare is enormous. It is the result of magnetic field lines snapping and reconnecting, similar to solar flares, but on a scale millions of times larger. These flares are unpredictable and rare, but when they occur, they reveal the enormous magnetic tension stored inside the star. The magnetic field of a magnetar is so strong that it distorts the shape of atoms. It can twist the crust. It can drive currents deep into the star's interior. And when these stresses build up over time, the release becomes violent enough to alter the magnetar's rotation slightly. Observing these flares allows scientists to study magnetic reconnection under conditions far more extreme than those found near the Sun. The radiation produced by neutron stars interacts with their environment in ways that reveal hidden structures. Pulsar wind nebulae, formed by the interaction of particle winds with surrounding gas, display stunning patterns. These nebulae glow in X-rays and radio waves, showing swirling jets, arcs, and ripples shaped by the pulsar's rotation. The Crab Nebula, powered by a pulsar, is one of the most dramatic examples. At its center lies a neutron star rotating 30 times per second. The energy released by this small star lights up a cloud more than 10 light-years across. The nebula pulses, expands, shifts, and glows with incredible complexity, all driven by a star only about 20 kilometers wide. This contrast between size and influence is one of the defining features of neutron stars. They are proof that even the smallest objects can reshape vast regions of space. The environments around neutron stars become even more dramatic when the star is part of a binary system. Accreting neutron stars produce X-ray emissions that vary over time based on the flow of material from the companion star. Sometimes the companion loses matter slowly, producing steady X-ray brightness. Other times, sudden bursts of material ignite nuclear reactions on the neutron star's surface. These X-ray bursts spread across the star in seconds, igniting layers of accreted material in rapid nuclear fusion. These bursts are among the fastest and most energetic thermonuclear events in the universe. They show how neutron stars can transform incoming matter into radiation with stunning efficiency. Accreting neutron stars also produce superbursts, which last much longer and release vastly more energy. These superbursts may be triggered by carbon ignition deep below the surface. The energy released by these reactions heats the entire outer layer of the neutron star, creating emissions that persist for hours. These long bursts provide valuable information about the star's interior structure and heating mechanisms. Observing these events allows scientists to measure how heat flows through the star, revealing the properties of neutron matter in different layers. Some neutron stars accrete matter in a way that produces steady X-ray emissions instead of bursts. These systems are known as X-ray pulsars. The accretion flow is channeled by the magnetic field onto the neutron star's magnetic poles. As the star rotates, the hotspots where matter lands produce pulses of X-rays. These pulses can vary in brightness based on the accretion rate, allowing scientists to study how magnetic and gravitational forces shape the motion of matter. Observing X-ray pulsars offers a unique view into the mechanisms that govern accretion, one of the most fundamental processes in high-energy astrophysics. In addition to electromagnetic radiation, neutron stars also play a major role in producing gravitational waves. Binary neutron star mergers generate some of the strongest gravitational wave signals ever detected. But even before merging, neutron stars influence each other through the tides they raise. These tidal forces distort the stars slightly, and these distortions change the gravitational wave signal. By analyzing these signals, scientists can measure the stiffness of neutron matter, an essential property that determines how compressible the star is. Understanding the stiffness of neutron matter helps determine whether neutron stars contain exotic particles or quark matter in their cores. These measurements bring us closer to solving one of the universe's biggest mysteries. What happens to matter at densities far beyond nuclear levels? Some neutron stars may even quake due to internal changes. These starquakes release bursts of energy similar to magnetar flares, but may occur in neutron stars with weaker magnetic fields. The crust adjusts slightly to relieve internal stresses, causing shifts in rotation or brightness. These quakes demonstrate that neutron stars are not static objects. Their internal pressures and forces shift over time, altering the structure of the crust and the alignment of magnetic fields. These changes are subtle but incredibly important for understanding how the star evolves over millions of years. Another mystery involving neutron stars is the origin of fast radio bursts, which are extremely brief but enormously powerful flashes of radio energy. Some fast radio bursts have been traced back to magnetars, confirming that at least some originate from neutron stars. But many fast radio bursts remain unexplained. They come from billions of light-years away and release as much energy in a millisecond as the sun does in a month. These bursts may be caused by magnetic field reconnection, crustal cracking, or interactions between magnetars and surrounding plasma. They may also involve processes not yet understood. The discovery of repeating fast radio bursts suggests that the underlying mechanism must be capable of producing energy repeatedly without destroying the source. Neutron stars, especially magnetars, fit this description well. Neutron stars also highlight the relationship between extreme environments and particle physics. Their magnetic fields accelerate particles to energies far beyond those achievable in laboratory accelerators. These high-energy particles travel through space, contributing to cosmic rays. Observing cosmic ray behavior helps scientists understand how neutron stars influence surrounding space. Their particle winds shape nebulae, heat surrounding gas, and create shock fronts that reveal the structure of magnetic fields. Cosmic rays may even carry signatures of exotic particles from neutron star interiors. The interplay between neutron stars and general relativity is equally fascinating. Neutron stars warp space so strongly that time runs slower near them. Their gravitational wells are deep enough to produce noticeable redshift in the light escaping from their surface. They produce measurable gravitational lensing effects, and their orbits in binary systems follow the curved geometry predicted by Einstein's equations. These effects allow scientists to test general relativity in some of the strongest gravitational fields accessible to observation. Neutron stars also help scientists explore the limits of rotational stability. Millisecond pulsars rotate so fast that they approach the breakup limit, the point where the centrifugal force at the equator becomes strong enough to tear the star apart. Observing these pulsars helps determine how rigid neutron matter is. It also reveals that the internal structure of the star plays a major role in determining how fast it can spin. If the core contains exotic forms of matter, the breakup limit might change. Studying these stars therefore helps probe the behavior of dense matter indirectly. The life cycles of neutron stars show that they never truly stop influencing their surroundings. Even after billions of years, a neutron star remains dense, massive, and gravitationally significant. Even when its magnetic field fades, its structure remains intact. Even when it stops emitting pulses, it carries within it the frozen history of a collapsed giant. Neutron stars continue drifting, interacting, merging, and cooling long after their visible activity ends. Their influence extends across cosmic timescales. They help forge heavy elements. They generate gravitational waves. They test the limits of relativity. They reveal quantum behavior on macroscopic scales. They demonstrate how matter behaves under unimaginable pressures. They remind us that even the remnants of stellar death can become engines of cosmic evolution. Neutron stars are extreme, unstable, violent, and yet astonishingly orderly. They are destructive, yet creative. They are small, yet powerful. They are rare, yet essential. And through their pulses, flares, collisions, and quiet drifting, neutron stars continue telling the story of how the universe pushes itself to the edge of what is possible. Neutron stars are among the few cosmic objects that reveal how the universe operates at its most intense settings. They bridge the gap between normal matter and the complete gravitational collapse of a black hole. They exist in a realm where particles behave in ways we cannot reproduce, where forces grow to unimaginable strengths, where gravity bends space until time itself slows. As we continue unraveling their mysteries, neutron stars expand our understanding of the universe, not by being large, but by being dense, concentrated, and fundamentally extreme. They show that the cosmos is not defined solely by size or scale, but by how energy and matter are organized. And nowhere are they organized more violently, more beautifully, or more mysteriously than in a neutron star. One of the most remarkable ways neutron stars reshape our understanding of physics is through their relationship with space-time. Because of their density, a neutron star's gravitational influence is colossal. Space around them is not flat, it is deeply curved. Time passes more slowly near their surface than it does far away. Light emitted from the star is stretched into longer wavelengths as it escapes the gravitational well. This gravitational redshift is not a theoretical idea. Astronomers have measured it. By analyzing the color and energy of photons emitted from neutron stars, scientists can determine how steep the gravitational well is and therefore estimate the star's radius and mass. These measurements help refine models of neutron matter and the exotic states deep inside the core. Neutron stars serve as the universe's most compact devices for bending space-time without collapsing into black holes. Their gravitational effects extend far beyond their immediate surface. A neutron star's gravity influences the motion of nearby stars, gas clouds, and dust. It alters orbits, redirects high-energy particles, and shapes the distribution of matter in its vicinity. In dense star clusters, a neutron star can exchange momentum with other stars, altering its velocity through gravitational interactions. This exchange can sometimes fling the neutron star out of the cluster entirely. Runaway neutron stars created this way can reach velocities of hundreds or even over 1,000 kilometers per second. They become high-speed travelers, crossing huge sections of the galaxy during their long lifetimes. Some may eventually escape the galaxy altogether, drifting through intergalactic space as lone ambassadors of stellar collapse. As neutron stars move through space, they continue to interact with the interstellar medium. Even though they emit little visible light, their radiation, particle winds, and magnetic fields carve patterns into the gas around them. Some solitary neutron stars create visible trails, bow shocks, that form where the star's motion compresses gas into a glowing arc. These structures act like footprints, marking the neutron star's passage through the galaxy. They reveal its speed, direction, and influence. Observing these trails helps scientists reconstruct a neutron star's past trajectory, connecting it to the supernova remnant from which it originated. Neutron stars also serve as cosmic accelerators. Their magnetic fields and rotational energy accelerate particles to near-light speeds. These particles escape into space as cosmic rays, some of which eventually reach Earth. Cosmic rays carry information about the environments where they originated, including the strength of magnetic fields and the intensity of particle collisions. Neutron stars contribute significantly to this cosmic radiation, shaping the energetic landscape of the galaxy. They show how compact objects can redistribute energy across enormous distances, far beyond their physical size. But neutron stars also demonstrate their power through their connection with the universe's most energetic events. Binary neutron star mergers produce gravitational waves, gamma-ray bursts, kilonova explosions, and heavy element synthesis. These events combine multiple physical phenomena: relativity, nuclear physics, magnetism, thermodynamics, into a single dramatic moment. Every collision between neutron stars is a cosmic event of enormous scale, reshaping the universe in ways that ripple across space and time. When gravitational waves from a neutron star merger reach Earth, they carry information about the star's masses, radii, spin states, and even the internal composition of their cores. These waves travel billions of years, crossing interstellar space unimpeded, carrying the story of a cosmic collision to detectors on our planet. The electromagnetic signals that accompany these collisions tell another part of the story. Gamma-ray bursts produced by neutron star mergers can outshine entire galaxies for brief periods. These bursts mark the moment when relativistic jets, streams of particles moving at nearly the speed of light, break through the debris cloud created during the merger. The jets emit intense radiation that fades quickly, but leaves behind traces detectable across multiple wavelengths. Observing these gamma-ray bursts gives scientists insight into how jets form, how magnetic fields shape their behavior, and how energy escapes from the densest environments in the universe. As the expanding debris from the merger cools, heavy elements begin to form. These elements, created through rapid neutron capture, become the building blocks of planetary systems. Gold, platinum, and many other heavy metals owe their origin to these cosmic collisions. The fact that everyday objects on Earth contain atoms forged in the heart of a neutron star merger shows how deeply connected we are to these extreme events. Neutron stars are not distant curiosities. They are part of the universe's cycle of creation and destruction. They seed galaxies with the ingredients needed for complexity. Without them, the periodic table would be far emptier, and life itself would lack essential elements. While mergers represent the dramatic end of some neutron stars, many spend their entire lives in relative quiet. They rotate, cool, drift, and slowly release the energy stored during their formation. Their pulses continue reaching Earth long after their magnetic fields weaken. Their crusts remain rigid for millions of years. Their interiors continue holding neutrons in superfluid states that defy classical physics. Even without bursts or collisions, an isolated neutron star remains a powerful object simply by existing. It is matter compressed to the edge of collapse. It is a fossil of a supernova and a probe into nuclear physics at extreme densities. Neutron stars also challenge our understanding of matter itself. The behavior of neutrons at such high densities is one of the biggest unsolved problems in physics. Scientists do not yet know exactly how neutrons interact when packed so tightly that they touch. They do not know whether the core contains exotic particles like hyperons or transitions into quark matter. They do not know whether neutron stars contain multiple phases layered inside, like cosmic onions. These unanswered questions keep neutron stars at the forefront of scientific research. Every observation, every pulse, flare, glitch, merger, and cooling curve adds another piece to the puzzle. Some neutron stars may host conditions so exotic that they contain forms of matter that cannot exist anywhere else in the universe. Quark stars, strange stars, and hybrid stars are theoretical possibilities that may resemble neutron stars, but with even more extreme internal states. If these objects exist, they could be identified through subtle differences in mass, radius, temperature, or gravitational wave signatures. Confirming their existence would revolutionize our understanding of high-density matter. Neutron stars therefore serve as stepping stones toward understanding even stranger cosmic objects. Their magnetic evolution also highlights the tension between stability and change. A neutron star's magnetic field is born in collapse, amplified by the shrinking core. It evolves over the star's lifetime, sometimes decaying smoothly, other times flaring violently. A weakening magnetic field may cause a pulsar to fade, while a sudden shift may cause a magnetar to flare. These processes show that the interior of a neutron star is constantly adjusting to maintain equilibrium. Even small internal changes can produce enormous amounts of energy. This ongoing evolution makes neutron stars dynamic, objects long after their formation. Through their entire life cycle, neutron stars influence the structure of galaxies. They produce supernova remnants that shape star formation. They distribute heavy elements into interstellar gas. They create gravitational disturbances that affect stellar orbits. They produce radiation that heats and ionizes surrounding material. Their mergers create shock waves that travel across galaxies. Their gravitational waves carry energy away from compact systems, reducing orbital distances over millions of years. Neutron stars, although small, participate in the large-scale dynamics of galaxies in ways that go far beyond their size. In the end, neutron stars remind us that the universe is built on extremes. It creates structures that stretch the imagination. It produces objects that defy ordinary intuition. It shapes matter into forms that break traditional physical rules. And it uses these extremes to build complexity, generate energy, and recycle material. Neutron stars show that the universe is not static but dynamic, constantly collapsing, igniting, merging, cooling, and transforming. They show us how stars die, how elements form, how gravity behaves near its limits, and how matter rearranges itself when crushed beyond atomic structure. They demonstrate the power of quantum mechanics on macroscopic scales. They reveal the flexibility of space-time under enormous stress. They are the boundary between the universe we understand and the universe we are still trying to comprehend. Neutron stars may be small, but their story is gigantic. They are the collapsed hearts of ancient giants. They are engines that power nebulae, clocks that measure the galaxy, and beacons that reveal gravitational waves. They are quiet travelers, violent colliders, and creators of the rarest elements. They are some of the most important objects the universe has ever built. And through their existence, they remind us that even the tiniest objects can hold the greatest mysteries and the greatest power.